Okay, this video will help you get started on the bonus for Pascal's triangle and the binomial theorem. So the first thing to understand is Pascal's triangle. And I've given you the first few rows of Pascal's triangle. The way the rows are generated, each row begins and ends with a 1. But the way you figure out the elements in between, it's the sum of the two numbers before. So the next element in this row would be 4. So I start with my 1 on the end, and the next element in the row would be 4. 1 plus 3 is 4. The next element would be 6. 3 plus 3 is 6. And then it's symmetric. Then the next element goes back 3 plus 1 is 4. And I will generate one more row for you on the video. So the row begins with 1, and the way I figure out what the next element is, 1 plus 4 is 5, and then 5 plus 6 is 10, or 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then the row ends with a positive 1. And now to analyze what I've given you, the power, I've got binomials a plus b raised to different powers. So let's just go through and list the powers of what's given. In the first row, the power is 0, a plus b raised to the 0 power. In the second row, it's to the first power. In the third row, it's to the second power. In the next row, it's to the third power. So the row that I've created would be a plus b raised to the fourth power. The row that I created the elements for would be a plus b to the fourth. And it's not large enough for me to really write and do a nice neat job with it here. Okay, coming back to the top, so I'm glad the first column is asking you to list the power. 0, 1, 2, 3, and we created the fourth. Now the row, this is where there are differing opinions as to how this would be explained, but the Algebra 2 book that our school uses labels the row the same as the power. So the row here would be row 0. So it's like you're starting the counting process with 0 instead of 1. A power of 0, a row of 0. The second row I would consider row number 1. The third row I would consider row number 2. The third row, or the fourth row, row number 3. And then the row that I created would be 4, counting with 0. Now, the column asking for the number of terms in a single row, well, how many elements are in a single row? Row 0 has 1 element. Row 1 has 2 elements, 1 and 1. Row 3 has 3 elements, 1, 2, and 1. The next row has 4 elements, 1, 3, 3, and 1. And finally, the row that I created has 5 elements, 1, 4, 6, 4, 1, 5 elements in that row. So you can see the relationship, the row number and the number of elements in a single row increases by 1. Now, the row that, or the column rather, that's asking you to expand the binomial, well, I have a plus b raised to the power of 0. Anything to the power of 0 is 1. The second, or row number 1, I have a plus b to the first. Well, a plus b to the first is just simply a plus b. A plus b squared is a squared plus 2ab plus b squared. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. And what you need to notice, let me erase over here a little bit to clean this up some. What you need to notice is that the elements in the row actually end up being the coefficients on the expansion. So row number 1, the only element is 1, and that is the expansion is 1. Row number 0, row number 1, a plus b to the first, well, the coefficient on a and b here is 1a plus 1b, but we don't write that. But you can see the elements in row 1 are 1 and 1. Look at a plus b squared. The elements in the row are 1, 2, 1. When you look at the expansion, 1a squared, 2ab, 1b squared. And if you care to prove the cubing, a plus b to the third power, well, the elements in that row are 1, 3, 3, 1. In my expansion, I have 1, 3, 3, and 1. So the relationship that you should take away from this is that the elements in the row of Pascal's triangle are the coefficients on the expansion of the binomial a plus b squared or cubed or to the fourth. So it gives you a more efficient, quicker way of determining the coefficients when you're raising to powers higher than 3. So that's just a nice accidental correlation here between Pascal's triangle and binomial expansions. So just a few rules to go through. Rule number 1, the coefficients of the expansion of a plus b to the nth power are the elements in row n of Pascal's triangle, meaning a plus b to the second would come from this row that we're calling row number 2. And we begin counting with row 0. So something to keep in mind that we begin counting with row 0. The second rule that's worth mentioning, the degree of each monomial, well, this we need to talk about for a second, the degree. The easiest and easier rule to see at the moment is that the number of terms in each row, or the number of terms in an expansion of degree n, you have n plus 1 terms. And it's easiest to see whenever you compare the power column with the number of terms. So when on the power is 0, I have 1 term in my expansion. When the power is 1, I have 2 terms in my expansion, and et cetera, the pattern holds throughout. What we do need to take a minute to talk about, however, is the degree of each term in the expansion. So let's look at, I think the easiest pattern to look at, I'm going to clear the board and I'm going to look at a plus b cubed. So if I expand a plus b cubed is 1a cubed plus 3a squared b to the first plus 3ab squared plus b cubed. And I'm doing this to show you what's happening in rule number 2. So if I go back to the first few weeks of school, whenever we were determining the degree of a monomial, remember a monomial is a single term. The degree of each monomial in this expansion, well, the degree, so I'll do a little degree in red across the top. The degree of a cubed is 3. The degree of a squared b, well, I would add 2 plus 1 and get 3. The degree of a to the first b squared is also 3, and the degree of b cubed is 3. So rule number 2 says the degree of each monomial in the expanded sum is degree n. And remember, my model I'm using is a plus b to the third power. So there's a little pattern that's occurring here, and we'll do an example on the other side to show you how the pattern falls out. And we'll do the sigma notation in a minute, but let me just go ahead and lay out the pattern. So turn to the other side, and let's practice a plus b to the fourth. And you would need that fourth row. So the elements of row 4, which we just created, the elements of row 4 are 1, 4, 6, 4, and 1. And that would be the row that I created with you. Now, the way to determine the powers, the power on A with the coefficient of 1 will be 4. And then you count down. So I'm raising a plus b to the fourth power, so a takes the power of 4. The next a term has a power of 3. The next a term has a power of 2, then a power of 1, and finally a power of 0. And then the power on b goes in the reverse order. B starts with the power of 0, and then you count up to the first, to the second, to the third, to the fourth. And then the way I pull together my expansion, the first term in my expansion has a coefficient of 1. So it's 1a to the fourth b to the 0. 1a to the fourth b to the 0. But I would simply write that as a to the fourth. I wouldn't write the coefficient of 1, and b to the 0 power is also positive 1. So my next term in the expansion will have a coefficient of 4, and it will be a cubed b to the first. The next term in my expansion has a coefficient of 6, and it's a squared b squared. The next term has the coefficient 4, a to the first, b cubed, and my last term has the coefficient of 1, a to the 0, b to the fourth, and once again I would simply just write b to the fourth power, since I would not write a coefficient of positive 1 and a to the 0 is positive 1. So that's the basic layout, that's the basic pattern that's created and the way you would determine the powers on each. So just looking at a few of what I've given you, if you're expanding a plus b to the fifth, you would need to create the fifth row, and remember starting with counting at 0, so technically that's really the sixth row, but if you make the row match the power, it's row 5. The number of terms in that expansion, you will have 6 terms in that expansion, and the degree on each term will be degree 5. If you're expanding a plus b to the 7th, you would use the 7th row. The number of terms in your row would be 8, and the degree on each term would be degree 7. If I'm expanding a plus b to the 8th power, I would use my 8th row. I would have 9 terms in my row, and the degree on each term would be degree 8. And let's go back and look at the expansion of a plus b to the 4th for a minute to talk about the degrees. The degree of the first term is 4. The degree on the second term is 3 plus 1, or 4. The degree on the third term is 2 plus 2, or 4. The degree on the fourth term is 1 plus 3. And then the degree on the last term is 4. And I'm expanding a plus b to the 4th, and I have 1, 2, 3, 4, 5 terms in my expansion. And I think that is enough for this video to get you started. You can see that the bonus is I'm asking you to provide the 9th, 10th, 11th, 12th, and 13th terms in the expansion of a plus b to the 20th. And then I'm also asking you to expand 4x plus 5 raised to the power of 6. And you're going to have to come to get a little bit of help on how to do that.